Today on day 4, we are going to take a look at how you write an equation of a line in vector form. So up until now, we've looked at a line, for example, y equals x plus 5. Our y-intercept is 5, and our slope is 1. So we go up 1 and over 1. So we have the coordinate 1, 6. Up 1 and over 1, we have 2, 7. Now, here's the deal. We're going to look at it in terms of vectors. So these vectors that are coming from the origin are called position vectors. So a position vector, it has the origin here. All right, so now we want to find a way to represent this line right here, this dot line, given in vector form. Okay, because we could see this line as vectors with different endpoints. So here's a vector, all these different endpoints connected make that line there. So our vector equation that will generate all of those points, we pick any point on the line. For example, this 1, 6 here. So, well, let's see. That is a position vector coming from the origin of 1, 6. Now we can take any vector along the line here. How do we get from 1, 6 to 2, 7? Well, we go over 1 and over 1. So that vector is 1, 1. Or how do we get from 2, 7 to 4, 9? 2 to 4 is 2, 7 to 9 is 2. Well, those are parallel vectors because they're scalar multiples. So we could use any of those there. He used P1, P0, and P1, so that vector is 1 to 1. Now, and we're going to call that our directional vector, okay? Okay, now to get to any other of those vectors, all we do is we can take this 1, 6 vector and we can add this directional vector multiple times. For example, to get up to this 4, 9, we could take our position vector of 1, 6, and then we'd add 1, 1, 1, 1, and 1, 1. And if we added those 1, 2, 3, 4, we'd have 4, 6, 7, 8, 9. If we wanted to go the other way, let's say we wanted to get here, we'd start with our vector 1, 6, but we would subtract 1, 1, minus 1, 1. So 1 minus 1 is 0, minus 1. So this is negative 1 and 4. So basically what we are doing is that equation for a vector line is in this form. We call it r equals, instead of y equals mx plus b, r equals a plus tb, where a, this vector right here, is any position vector that's on the line, plus t, however many of times, and this is our directional vector. So it seems complicated, but think of it as like y equals that mx plus b. Here's, how many times our slope. That's kind of like our directional vector. And our position vector, that's just any point on the line, like it was, well, our y-intercept was a specific point, but just any position vector will do. So let's take a look here. We are given 2 coordinates here. So basically, if here's our origin, and I'm terrible at drawing in 3D here, but we're given these 2. So we need a line that runs through this. And so we have our 2, these could be 2 position vectors that we're given. This would be A and B. So we have to find, what is that directional vector? So our directional vector here, let's see, 1 to negative 2. So that's going down 3, 0 to 4, 0 to 1, over 1, negative 4 to 1 is down 5. So there's our directional. So our equation, we could choose this one, 1, 0, negative 4, plus t, negative 3, 1, and negative 5. Or, if we wanted to, we could use the other coordinate. We could use negative 2, 1, and 1, plus t, -3, 1, and -5. You could use either one. It doesn't matter there. So this next one here, find the equation of a line parallel to A and passing through the point B with position vector B. Well, this is the exact same thing. It's just telling us that this is our position and it's parallel to this, so this is our directional right here. So we could have R equals our position, -1, 2, plus T times 3, 2. Now the next two get a little bit more complicated. Not much, but just a little. We added another step for this one. We want it to be perpendicular to this vector, and this is our position vector. So in that equation, we have our position vector. We know that. But we have to figure out, T's and plus signs look the same. We have to figure out that perpendicular part right there. So, well, it's perpendicular to this, so we don't know what that is. So let's just say it's any x and y. Some xy vector that's perpendicular. So we know the dot product here has to equal 0. So 5 times x plus -2y has to equal 0. So 5x minus 2y equals 0. So we just have to come up with, there's two values here that would work, and there's tons that would work in this equation. Excuse me, let me rephrase that. An x and a y value that would make the statement true, and there's lots of those, but I just look at an easy one here. Well, let's see, if x is 2, this would be 10, we'd have to subtract 10, so y would have to be 5. So a perpendicular vector would be 2, 5. But again, there's lots of different combinations that would work there. All right, so there you had, I kind of skipped past the answer there, but there you have your equation right here. Now this last one, determine whether a given point lies on the line. All right, well here's our vector equation, and if we want to know if 5, -2 lies on the line, well what is that x, our x part of this, our x coordinate would be x equals 5 plus 1t, that's the top part. And our y value would be 1 plus 2t, because y is on the bottom. So does this hold true? Does our x value that we have on our point, does 5 equal 5 plus 1t? Well, what is our time? What is t when it gets there? So 0 equals 1t. So t equals 0. Okay, and let's see, what about y? When we plug in our y value, -2 equals 1 plus 2t. Minus 1. So t equals -3 over 2. So that's not the same. That's kind of like on our picture saying, you know, how many vectors do we need to move over to get there? It's saying, well, for our x coordinate, we only need to move 0. But our y was -2/3. So that's not the same. So this would not lie on the line. Because this one's saying we, you know, go our position vector, we go over 1 and up 5. And then it's saying we don't add anything, and that makes sense because this would be the coordinate 1, 5. Or excuse me, 5, 1, my bad, x, y. Let me draw that again. So we go over 5 and up 1. So there's our position vector, and it's saying to get to this coordinate, we don't go any of the directional vector, and that makes sense. But it's saying to get to the y value, we have to move a directional vector backwards. So it's not the same for x and y, so it's not on the line. Well, now in 3D, what do we have? We have our x is -1 plus 1t. Our y is 5 plus 0t. And our z would be -3 plus, that would be minus 2t. So let's see if this holds true. Here's our directional vector. Well, let's see, to get x of -3, -1 plus 1t. So t would be -2. So our directional vector, we'd have to move it backwards twice. For our y value, 5 equals 5 plus 0t. So 0 equals 0t. Well, that would hold true for any value of t. because 0 times negative 2 is still 0, so that would work. And then we have 1 equals negative 3 minus 2t plus 3. 4 equals negative 2t. So once again, t would be negative 2. So that works because we have our directional vector, and then it's saying to get to this point, we'd have to move here is our, I get those confused, position vector. And it's saying to get to that coordinate, we have to move our directional vector. We'd go in the opposite direction twice. So it is on that line.